Next, let's move on to adjacency lists. And the good thing in my opinion is that these are much more simple to run an algorithm on rather than on a matrix. Now, originally we talked about the idea of having a graph node class or an object for an adjacency list where, we're storing some kind of value. It could be a string, a character, an integer, and then it's also going to have a list of neighbors. The neighbors are going to be pointers. They could be directed or undirected, but essentially they're going to be pointers pointing at other nodes. That's one way to do it. And if we were actually creating our own graph, we would do something like that. But when it comes to coding interviews, it's actually much more common to just use a hash map to represent an adjacency list. Because as you can see, there's two things we care about: the value, or the ID of each node, as long as that is unique. And for coding interviews, it's almost always unique. Each graph will have something that uniquely identifies it, whether it's an integer or a character or a string. In this case, let's say we have a character A. And so that's going to be the key of our hash map. So this is how I'm doing it in Python. But the important thing here is that this is the key. The character is the key. And the value for that key is going to be a list. And that list is going to represent the neighbors. So this is just an example adjacency list where we have two nodes, A and B. Now the lists here are empty, so that basically means there aren't any pointers. That's just a very simple example just to kind of show you that this same idea can be represented using a hash map. Now let's actually do a very common algorithm when it comes to coding interviews, which is usually you're not just given the adjacency list itself, you have to build it yourself. You are given enough information to build it though. So the most common thing is you're given a list of edges. In this case, these are directed edges, and we want to build an adjacency list with them. What does directed mean again? Well, for this edge, we're basically saying that there exists some edge going from A to B. So it's directed. So it's going from A to B. This is what it would look like in terms of the picture. Now how do we go about actually building the adjacency list? Well, let's just first declare a variable. This is, let's say, an empty hash map. We're going through every single edge, which is a pair of nodes here. The values are, the identifiers for that node. So we're calling it, in this case, source destination. So source is going to be the first of the pair, and the destination is going to be the second of the pair. This is how you would do it in Python, but other languages will also be provided below. So one thing is that our hash map is empty, so these keys might not even be in the hash map itself. So if they're not, that's what we want to do. So we're first going to check, is source not in the adjacency list? Is this key not in the hash map? If it's not, let's add it to the hash map and give it a value of an empty array. So the neighbors are, initially empty. We just added this node to the adjacency list. We're going to do the same thing with the destination, even though we're not going to be adding anything to the array of the destination neighbors, because we want to, at the very least, make sure that every node that we saw in the list of edges is added to the adjacency list, even if it doesn't have any neighbors, because we want to at least have an empty list to confirm it doesn't have any neighbors. So here, what we would say is for the adjacency list of the source, for our first example, that would be A, we're going to append to its neighbors, which initially is an empty list, we're going to append B. So visually, we would say A points at B. It has a neighbor B. Going to the second edge, we would do the same thing. B, though, in this case, has already been added to the adjacency list. We did that previously with this line. But C is not, so we add C to the adjacency list. It doesn't have any neighbors, though, of course, just yet at least. But now we know B points at C, so we have an edge going from B to C. And then third edge, B to E, we're going to do the same thing. Put an edge over here, C to E. That means there's an edge going like this, and E to D. So there is an edge going like this. So this is what the graph would look like. We were given all the information we needed. We were given the edges, but from the edges, we could imply what the nodes are. And then we have a representation that looks like this. This is the same information that would be stored in our adjacency list, which, we're using a hash map to do that. And you can see why, because it gives us all we really need. Now let's move on to actually running some common algorithms like DFS and BFS on adjacency lists. And the good thing is these are a little bit easier than doing them on a matrix. So let's run pretty much the same algorithm we did on the matrix using DFS, depth first search. We want to count all the paths, and again, this is going to be a backtracking algorithm, but the code is a lot more simple, mostly because we don't have 1,000 edge cases to worry about. We don't have to worry about going out of bounds. That's what makes adjacency lists nice. So assuming we're given this input, that's our adjacency list, and assuming it was given in the form of a hash map in Python, we're going to run DFS, count the paths. Let's say the starting node is going to be A in our DFS, and the target node is going to be E. So we want to count the paths from A to E. The adjacency list is passed in, and we also have a hash set, which is going to keep track of visited nodes along a single path, just like we did with a matrix. So that hash set is passed in. We're going to call this function and then print whatever it returns. So starting at A, we check, has this node already been visited? If it has, there's 0 paths from here to the result. It's not the case though. Well, is this node already the target? If it is, then that means we found a path to the target. We can return 1. It's not E, so it's not the target. Then we declare a variable to count how many paths from A to E. We add the node to the visit hash set and we go through its list of neighbors. The good thing here is it's so easy to iterate through the list of neighbors because we have it in our adjacency list. We don't have to go, manually in 4 different directions. That's really annoying to write out. So we call DFS on each of the neighbor nodes. Now, maybe A doesn't even have any neighbors. That would be an empty list, an empty array, and then this for loop would never even execute. But in this case, A does have 1 neighbor. So we were at A, now we're gonna be at B. I'm using these arrows to kind of indicate which node that we've already visited and which node we're currently at. So we're at B right now. So recursively, we're at B. Is this node already been visited? Nope. Is this node the target? Nope. So now we're counting how many paths from B to E. So that will be 0 initially. We'll add B to the visit hash set and go through the neighbors of B. It actually has 2 neighbors, C and E. Let's say we call DFS on C first. Notice how it's DFS, not BFS. That means we're going as deep as we can in one direction. So we get to C. This is not visited already, and it's not the target. So we count paths from C to the target, and we add C to visit hash set, and we go through its list of neighbors. It only has a single neighbor. So then we call DFS on E. Now we are at E. It's not been visited already, but it is the target node. So we return 1 in this case. That means we found this path that leads to E. So we return 1. This is the base case. So we return 1, we backtrack, and then we end up back at C. From C, we called DFS on E, it returned 1, we add 1 to our count, and then this loop is going to stop because we only had 1 neighbor from C. So then we're going to backtrack now. From visit, we're going to remove C. So you can think of that as, removing this pointer. And then we're going to return the count, which is 1, and that 1 is going to be returned back to B. And then from B's perspective, we're going to take that result, 1, add it to its count. So its count is now 1. But for B, it actually has a second neighbor. It has the neighbor E. So we're going to call DFS now on E from B. So pointer here again, same base case is going to execute. Now we found another path that looks like this. So we return 1 from E, we add that 1 to our count for B, which is 2. So we know there's 2 paths from B to E. And then that's its last neighbor. So then we're going to remove B from the visit. So you can think of that as removing this pointer. And that's kind of the backtracking part. And then 2 is going to be returned back up to A. So 2 is over here. And then A only had a single neighbor, so its loop is going to stop and it's going to end up returning 2. So there were 2 paths from A to E. Now we didn't even end up visiting D. That's because we didn't need to. Whenever we get to the target, we're going to immediately stop. So you can see that this is much more simple than running it on a matrix. But the core ideas are definitely the same. We have some base cases. We want to, enumerate every single possible path. And if we end up visiting a node, then we want to stop. Now, in this case, we never visited the same node twice along a single path, But for example, suppose that from C, there was actually a pointer back to B. In that case, let's say we do a DFS, we get to A, then we get to B, then we get to C, and then from C, we have two choices. We can go to E, or we can go back to B. But if we did that, we went back to B, we'd see, well, we've already visited this once along this path, so we can't just visit it again. So at that point, we would end up returning 0 from there. We'd say that there's 0 paths going to the target where we start at B, come to C, and then go back to B. There's 0 valid paths doing it like that. So it can get complicated to analyze the time complexity of this type of brute force backtracking DFS approach. So I'll try to keep it simple. We know that at any given path, we know that we're going to go through every single possible path in the entire graph. I mean, we have to count the paths. So that could be the worst case. The length of a path is going to be no larger than the number of vertices that we have, because we can only visit each vertice once along a given path. So that is going to kind of represent the height of our decision tree. Now for each vertex, how many choices could we have? In the worst case, it would be, every vertex is connected to every other vertex. So that would mean V choices. But we're going to say, let's just use some value n, where n is the average number of edges that each node has. This is a slightly more common way of talking about it. But the important thing is just kind of understanding the ideas that I'm talking about here, understanding the ideas of choices and how long could a path be and stuff like that. So the height, again, of this decision tree, when I say decision tree, I mean, all the decisions that we could make when we're counting the paths on this graph. The height is going to be V. The number of choices we could make is going to be N, where N is, let's say, the average number of edges that each vertex has. So in that case, the time complexity, analyzing this the same way that we did a binary tree, is going to be something like N to the power of V. So big O of N to the power of V. Now, it's pretty rare to actually have to analyze the time complexity this type of way, but the important thing to recognize here is that this DFS, this backtracking, is not going to be very efficient. Just like most backtracking algorithms, this is exponential. We know it's exponential because the power here is going to be a variable. If we had n squared, that's not the end of the world because the power is a constant value. Even n cubed wouldn't be that bad. But here, as the size of our graph grows, which is V, this time complexity is going to grow extremely quickly. So this is very, very inefficient. BFS is much more efficient, as we will see. So let's take a look at the same example problem. Let's try to find the shortest path from a node to a target. So in this case, the starting is going to be A again, and the target is going to be E. Those are the parameters we're passing in, and we're passing in the adjacency list that we built, for this representation. Now the BFS is going to work similar to the matrix. We're going to initialize a few variables. The length is initially going to be 0. We're going to have a hash set, and we're going to add the starting node as visited to that hash set, and we're going to have a queue, and we're going to add that starting node to the queue. So that's the first level in our BFS. So while our queue is not empty, we have a single node in our queue right now. We're going to iterate through the length of that queue at that given moment. So we're going to take a snapshot of the length. It's 1. So we're going to run this loop 1 time, and we're going to pop 1 node. So we pop that node. This is our current. We're going to check, is it equal to the target? If it is, we can return the length, which is initially 0. So we're saying, the length from starting here to arriving here is 0. That would make sense, but this is not the target. So we go through its list of neighbors the same way we did earlier, but we check, is this neighbor not already visited? If that's the case, we can add it to visit, and we can add it to the queue. But if it is already visited, then we don't do either of those things. In this case, it has one neighbor, B, and yes, we're going to add this to the queue and add it to visit. So then this loop will stop, and this loop will also stop because we went through every node in the queue at that point, and then we can increment our length. So we know it took a length 1 to arrive at this level. Next, we check, are we still executing the while loop? Well, our queue is not empty, so we are. We're going to take a snapshot of the length of the queue. It's 1. It's just one node. So we're going to run this loop once. We're going to pop this node. It's not the target, so we're not going to return. We're going to go through its list of neighbors. It has 2 neighbors, and each of them have not already been visited. So we're going to add both of them to the visit hash set and add them to the queue. And then we're going to increment our length by 1. So it took a path length of 2 to get to this layer or this level of the graph. And now we're gonna run the while loop again. We're gonna start going through both of these nodes. We're gonna take a snapshot of this queue. It's gonna be of length 2 because there's 2 of these here. We're gonna pop them. Let's say we pop C first. We would pop it. We would check it's the target. Nope. We would go through its list of neighbors. It has a single neighbor, which is E. We would check, has it already been added to visit? Yes, it has. So we're not going to add it again. Then we're going to end up popping the next one, which this is the only one remaining. We pop this. Is it equal to the result? Yes, it is. So we return the length. It's 2. That means that the shortest path was length 2. And we know that because we went layer by layer. These are all the nodes we could reach with a path length of 0. These are all the nodes we could reach with a path length of 1. These are all the nodes we could reach with a path length of 2. And this is the first time we encountered the result node. So the shortest path to that node must be 2. And that's what we return. Now here, the time complexity is going to be the same as earlier. It's going to be the size of the graph. But earlier we talked about for a matrix, the size of the graph was n times m. And technically what we didn't account for when we were doing that were the edges. This is the number of nodes in the matrix graph, but the number of edges for each node was 4. So technically the time complexity for running BFS on a matrix is 4 times n times m, but we know we don't care about constants. So this is the time complexity we get here. But in this case, let's say the number of nodes is actually v for vertices, right? So that's the size of the graph. But how many edges could each node have? Well, technically v, right? Because remember, we learned earlier that e is going to be less than or equal to v squared because each vertex could have v edges. So if we're talking about edges for each node multiplied by the total number of nodes, it could be v times v, which is equal to v squared. But we don't write it this way because we know for sure here that's not necessarily the case. This is not a full graph where every single node has the maximum number of edges. So to be more accurate, we could say the size of this graph is actually v, which is the number of vertices, because we potentially will have to visit every single one of these. In the worst case with our BFS, we'll have to add each of the vertices to our visit hash set, but we might also have to travel along every single edge, which may not necessarily be equal to v. It could be greater or it could be less. So to be more accurate, we say that the time complexity for this BFS is equal to v plus e, where e is the number of edges in the graph. The space complexity, though, is a bit more simple. We know in the worst case, we could add every single node to the visit hash set and every single node to the queue. So the memory complexity is going to be big O of v, where that's the number of vertices, of course. Now, before we finish up with graphs, I want to mention that we definitely learned a lot here, and that's because graphs are a very, very big topic in general, but also for coding interviews. They're a topic that comes up very frequently. But one thing we didn't talk about is what if these edges actually have some kind of weight attached to them? For example, the length of, this edge is not just 1. We've kind of been assuming each of these edges has the same length. We treat them the same. But what if, the same way how cities are connected by roads that could be of different length, what if the length of this was 2, this was 3, this was also 3, and maybe this one is 10? What would be the shortest path in that case? It would have been this over here, not what we had. We said the opposite. We said this is the shortest path. So our algorithm here would get that wrong. There is a much more complicated algorithm that could account for edges that have some weight or value attached to them. And if you want to learn more about it, I recommend checking out the Advanced Algorithms course. There's actually tons of graph algorithms that we didn't talk about, but they can get very, very complicated. There's a lot of academic research that's actually gone on in graphs. These are really complicated structures. But I think understanding DFS and BFS gives you a really, really strong foundation. After all, the shortest path algorithm that could solve this problem is actually based on BFS anyway. It's just a modified version. If you'd like to practice some graph problems, I recommend checking out the practice section and going to the graphs topic.